Hello students, in this lecture we'll start linear beam tubes, also called as O-type tubes. In the previous lecture we have taken limitations of conventional tubes. So there are certain limitations of conventional tubes. That is, first is the inter-electrode capacitance, lead inductance effect, transit time effect, gain bandwidth limitation, then effect of RF losses and effect due to radiation losses. So these are the limitations or disadvantages of conventional tubes. So beyond the 100 megahertz, we can't use these conventional tubes, and due to this we will use Klystron type tubes, or generally called as O type tubes. Okay, so these disadvantages or limitations are removed in the Klystron tubes, or in O type tubes. Next, so the conventional vacuum tubes such as triode, tetrodes, and pentodes are still used as a signal source of a low output power at low microwave frequency. The most important microwave tubes at present are linear beam tubes, also called as O-type tubes. The paramount O-type tube is a two-cavity klystron, and it is followed by the reflex klystron. Okay, so O indicates the original. So classification of linear beam tubes. So in your syllabus there is a classification. So linear beam tubes or O-type tubes classification. It is divided into two types, that is cavity type and slow wave structure. Cavity type is again divided into resonance structure, and this slow wave structure is again divided into the forward wave and backward wave. This resonant cavity are two cavity klystron or reflex klystron, and in this forward wave structure, generally helix traveling wave tube or couple cavity traveling wave tubes are used. And in backward wave, generally backward wave oscillate amplifier or backward wave oscillators are there. And this Klystron is a combination or a hybrid model of Klystron plus TWT. Okay, so this is a tree diagram. You can keep in mind if a question is asked, give classification of O-type tubes. Okay, so we have explained the tree diagram, so we'll skip this slide. So two cavity klystron structure is as shown in this figure. So two cavity klystron consists of heating element, then it consists of cathode, then focusing electrode, anode, then next is there are two cavities, buncher cavity and catcher cavity. Okay, and this RF input is given to this side, from this side. Okay, and space between them is called as a drip space. Okay, space between two cavities is called as a drip space, and when electrons are emitted, this space is called as an interaction space. Okay, and this is called as electron bunches. Okay, electron bunching process takes place. Okay, so this heating element or cathode emits the electrons, and these emitted electrons passes through this buncher cavity. Okay, and during passing, these electrons bunches are mixed with each other to form the bunches, and these electrons are comes towards this we can say collector, and also some of the bunches, that is we get RF amplified output from this side, and these are the magnet systems used in this uh, two cavity klystron. So in the construction we will see in detail. So this is a other uh, two cavity klystron diagram. You can draw previous diagram or this diagram in exam. So representation: cathode is there, anode, buncher cavity, catcher cavity. These are the bunched electron. Space between them is called as a drip space, and this is a collector. Okay, so next, in more detailed construction, we can observe this is the internal structure of a two cavity klystron amplifier. RF input is given from this side. This is a cathode, this is anode, then buncher cavity, catcher cavity, and this red shows the bunching effect, and these electrons collected at collector, and we get amplified output from this side. So in construction, as we have already seen, there are two cavities, that is a buncher and catcher cavity. Electron gun comprises cathode, heating element, and anode. The electron beam is produced by cathode by making use of heating element, and the high positive potential at the anode provides required acceleration to the electron beam initially. As previously mentioned, region between two cavities, that is buncher cavity and catcher cavity, is known as a drip space. To allow focused propagation of electron beam inside the tube, an external electromagnetic winding is used that generates a longitudinal magnetic field. This is done in order to prevent the spreading of the beam inside the tube. The amplified RF signal is achieved at the catcher cavity. Also, a collector is present near a second cavity that collects the electron bunch. So in working principle, so two cavity klystron is widely used microwave amplifier operated by principle of velocity and current modulation. So this diagram with the help of these sentences are very important. When all the electrons injected from the cathode arrive at the first cavity with uniform velocity, those electrons passing the cavity gap at zero of the gap voltage or signal voltage passes through with unchanged velocity. So this sentence is important. Electrons passing the first cavity. These electrons passing the first cavity at zero of the gap voltage. When gap voltage is a zero, then zero cavity at zero of the gap voltage passes through with unchanged velocity. When gap voltage is zero, there is an unchanged velocity, that is velocity is a constant. Those passing through the positive half cycle of the gap voltage undergo increase in velocity. Those undergo positive half cycle of the gap voltage, uh, then undergo an increase in velocity, and those passing through the negative swings of the gap voltage undergo decrease in velocity. So there is a variation in velocity in a drip space. So you can mention if this is a signal. Okay, when gap voltage is zero, previous case is a first case is when gap voltage or cavity gap at zero, then that is a first cavity gap at zero of the gap voltage pass with unchanged velocity. Means when gap voltage is zero, here with zero voltage, then electrons passes directly, there is no change in velocity. Then those passes through positive half cycle of the gap voltage. So this is a positive half cycle of a gap voltage, or a positive half cycle of the gap voltage undergo an increase in velocity. So during positive half cycle there is an increase in velocity, but in a negative half cycle there is a decreasing in velocity. There is a decreasing in velocity. So when gap voltage is zero, electrons passes through unchanged velocity, and when during positive half cycle of gap voltage, velocity increases, and during negative half cycle of the gap voltage, velocity decreases. Means there is a variation in velocity, electron velocity in a drip space, and when there is variation in electron velocity in drip space, that is called as velocity modulation. So in oral exam, question is asked, what is velocity modulation? So you can write or you can explain at that time, that is as the result of these actions, that the electrons gradually bunch together, they travel down the drip space. The variation in electron velocity in drip space is known as a velocity modulation. The density of electrons in the second cavity gap varies clinically with time. The electron beam contains an AC component and is said to be current modulated. Okay, so this velocity modulation and current modulation process is important in the two cavity klystron. Again, in detail, we can explain working principle. Previous slide you can mention in explanation. You can add if you have more time. Initially, electrons are emitted from the electron gun, and anode present in the structure provides desired acceleration to the beam. In the absence of any RF input, that is a gap voltage is zero, the electron will tend to move with their respective uniform velocity to reach the catcher cavity and gets collected. But when external RF signal is applied at the input of the buncher cavity, then this causes the generation of local electric field inside the tube. This electric field causes the bunching of electrons as the field applies acceleration and deceleration. In acceleration, there is increasing in velocity, and in deceleration, there is a uh, uh, decrease in velocity. In acceleration, increasing in velocity; in deceleration, decrease in velocity to the moving electron according to the polarity of the signal by which the field is generated. Basically, the reason for causing acceleration and deceleration is that when the direction of movement of electron is opposite to the direction of the field, then in this case electrons experience a decrease in their moving velocity. However, if the generated electric field and the direction of movement of the electron are same, then in this case electrons experience increase in the velocity of their movement. So in the previous slide we have also explained this working. So the maximum bunching should occur approximately midway between second cavity grid. Okay, this is important sentence. Where maximum bunching occur approximately midway between second cavity grid during its retarding phase. Thus, the kinetic energy is transferred from the electron to the field of a second cavity. It is a kinetic energy is transferred from electron to the field of second cavity, and we will get the amplified output at the catcher cavity. The electrons then emerge from second cavity with reduced velocity and finally terminate at the collector. The characteristics of a two-cavity crystal are as follows. Efficiency is about 40%. Power output, that is average power or CW power, is up to 500 kilowatt, and pulse power is up to 30 milliwatt at 10 gigahertz. Power gain is about 30 dB. So this is an apple gate diagram, and in exam explain two cavity Klystron working principle with apple gate diagram. So as previously mentioned, at positive half cycle and negative half cycle, how bunching of that electrons takes place in a drip space, we have to explain. So first gap and second gap here shown, and this is a gap A, you can say, and these are the bunching limits. X, Y, Z. We have to consider Y as a reference electron. Then this X is an early electron and Z is a late electron denoted by Z. So we will start explanation of this applicate diagram. Consider when there is no voltage across the gap. When there is no voltage across the gap, that is a here there is a no voltage, that is gap voltage is a zero. Uh, the electrons passing the gap are not affected and continue to the collector with same constant velocity. Electron passing through the gap and there is a constant velocity. When an input is applied to the buncher cavity, an electron will pass through gap A at the time when the voltage across this gap is a zero, and going positive, let this be the reference electron Y. So this is a reference electron, and going positive here, this reference electron is unaffected by the gap, and thus it is shown with the same slope on the applicate diagram. So this is shown in same slope as shown in this diagram. uh, Electrons passing the gap before any signal was applied to the buncher cavity. So here this is Y is a reference electron, and here when the voltage across this gap is zero and going positive, let this is a reference electron Y. When voltage across gap is zero and going positive, then we have to consider this electron as a Y. Then next is electron Z. So it is called as a late electron. Electrons Z passes the gap A slightly later than Y. okay, of slightly later than the y this z passes. In the absence of gap voltage, both the electrons would have continued past the gap with unchanged velocity. In presence of positive voltage across gap A, observe here, in presence of, this is a positive gap voltage, um, okay. However, uh, unchanged velocity, in the presence of positive voltage across gap A, however, the electron Z is accelerated slightly and given enough time and will catch up with the reference electron. So this electron catch up with this Y electron, okay. Catch up with this reference electron easily before gap B is approached. Then similarly, electron X passes through gap A slightly before the reference electron. So this is a X electron which is slightly before this Y electron. It is also called as an early electron. Okay, and is retarded by negative voltage. Observe here, voltage is a negative, Z electron voltage is positive, and Y is also going to positive, but here X is at a negative voltage, okay, and is retarded by negative voltage at that instant across the gap. Since electron Y was not so retarded, it has an excellent chance of catching electron X. So uh, excellent chance of catching electron X, okay. So since electron Y is not retarded, this Y is not retarded, therefore it has an excellent chance of catching electron X. So X and Y catches each other, catching electron X before the gap B. This is shown in Applegate diagram. As shown in this Applegate diagram, there is a bunching is formed. As a result of action, the electrons gradually bunch together as they travel down the drip space. The variation in electron velocity in drip space is known as velocity modulation, and density of electron in the second cavity is also shown here, okay. So this is a Applegate diagram, very easy explanation. We have to show these three electrons. Central electron, we have to mention it as a Y, and we have to take it as a reference. Y को reference लेना है, okay. And when gap voltage is 0 and going positive, there is no change in that electron. Then after that, Z electron is passes, which is a later than Y. Therefore, Z catches with Y and going positive, Z is going positive. Then next, before that Y electron, X electron is early, that is passing, and which is at a negative voltage as shown in this figure, at negative. Therefore they catches with each other, that is X Y Z, and X Y Z catches with each other and form a bunch of electron, and this electron bunch passes through the interaction phase, and more bunching effect is at cavity B, and therefore that is a catcher cavity, and we will get the amplified output at the catcher cavity. So next is a multi-cavity klystron. In all modes, modern klystron, the number of cavities exceeds 2. A large number of cavities may be used to increase the gain of the klystron or to increase the bandwidth. So this is a example of a multi-cavity klystron, that is a 3-cavity klystron. That is this is a first cavity, second cavity, and third cavity. Okay. The next applications of two-cavity klystron, it is used in a UHF TV transmitters, in a troposphere scatter transmitters, in satellite communication ground stations, in radar transmitters, and also used as a power oscillator between 5 to 50 gigahertz if used as a klystron amplifier. So these are the applications of the two-cavity klystron. Thank you. So in this lecture, we have taken a two-cavity klystron. In that, we have taken a construction, working principle, and also working principle with the Applegate diagram. So keep in mind that Applegate diagram, in sometimes overall exam, draw the Applegate diagram. Such type of a question is asked. Also, what is velocity modulation? What is current modulation? What are the number of cavities present in two cavity klystron, that is a buncher cavity and catcher cavity, okay. So such type of questions are asked. So very interesting topic, and you can solve it at in a exam also. Okay.